Okay, let's go ahead and get started. I've got your quizzes. I'll try and hand those back maybe while we work some problems during the class. Um, what have we got going on this week? We've got a quiz on Friday. I have a help session. We'll have a help session on Thursday before the quiz, Thursday night at 7:30 p.m. On Google Meet. Okay, and the link for that is in the syllabus. And I'm available Monday, Wednesday, 1 to 5 p.m. office hours by appointment, where the appointment is just tell me after class, okay? That you want to do it. Questions on things going on in the class? Okay. Hope you guys had a good weekend. Somewhat restful maybe, or rejuvenating. I want to talk about a couple concepts that one of the other professors emailed me and said that you were going to be using diamagnetic and paramagnetic, the concepts of diamagnetic and paramagnetic in lab, and we know everything we need to know for those for the most part. So paramagnetic, Great. Paramagnetic. If an atom is or an element is paramagnetic, that means that it has unpaired electrons. And it means it is attracted to a magnet. Okay, this is not, it is a magnet, which is, what happens with ferromagnetism, which is something different. If it doesn't have unpaired electrons, we call it diamagnetic. Okay, it has no unpaired electrons. Okay, and it is slightly repelled by a magnet. All right, and I think in your lab this week, you're probably going to you're going to do electron energy diagrams. We'll do another one here just to remind you, but you'll do electron energy diagrams, and doing that, you will determine whether there are unpaired electrons in a given element or a given sample. You can do it with compounds too, I think. And then you're going to put it into, there are special balances that have magnets in them. And so you weigh something and you can tell it weighs more if it's pulled towards the field, or maybe it weighs less. I haven't used one since undergrad, but I have heard other faculty mention one, so I'm pretty sure you're going to be using one in lab. So let's see, how would we determine this then? This is where we use our electron energy diagrams. Let's do an electron, so let's say we had a sample of copper. Is copper, the element, diamagnetic or paramagnetic? All right, well, the way we would figure this out is we would draw an electron energy diagram for copper. And this is the one where we have the lines and we put the electrons in. So first thing I'm going to do is, I'm lazy, so I don't really want to draw all the electrons here. So if I'm copper, if I want to do the shortcut, what is the shortcut called? Noble gas configuration, correct. And so which noble gas am I going to write down before I do copper? Copper is Cu, it is 29. Argon, right. So I'm going to start with argon. I just saved myself a bunch of time. Okay, why is that valid? Why can we do that? If we're trying to think about some property of copper, why do I not care about any of the electrons that would fill the shells argon and below? Because they're full shell, they're inner shell electrons is what it is, okay? So chemistry is about electrons, All right, and the electrons that touch the outside world are the ones that aren't in those inner shells. They're in the outer shells. And I'm going to give you a new term today that we haven't been using. We call those valence electrons, the outer shell electrons. Okay, they're valence electrons. I'll define it later. So now what am I going to do? I need to fill this in. And like always, I'm just going to use the periodic table. Okay, I'm in argon. All right, so I wrote argon, and now I'm going to fill in. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 electrons are going to go in here. These are my S, right? And we're down 1, 2, 3, 4, 4s. And then this is where it's a little tricky, where you want to use that diagonal diagram. These are actually the 3D. Okay? So we're going to go 4s, then 3D. So 4s, how many orbitals does the S subshell have? Just one, right? So we're going to have one here. I'm going to write it 4s. These should be arranged vertically because we're trying to demonstrate energy. Energy goes up as we go this way. We fill from the bottom energy to the top. And electrons are going to sink down to the lowest energy level. So we had 11, right? So we're going to go 1, 2, okay? And then we're going to do our 3D. How many electrons does a D subshell have? Or how many orbitals, I mean? 5, right. So 1, 2, 3, 4, 5. And now I'm going to fill, and I have 9 left, right? I had 11. 1, 2, 3, 4, 5. I did it like this because they don't like to pair up unless they have to, right? So I unpaired, put them in unpaired. 6, 7, 8, 9. Does copper have any unpaired electrons? Yes, it has 1. That's enough. That is going to be paramagnetic. Questions on how we do that? Yes.
Could you just go back up to the definitions?
Yes. Okay. Yes.
When do we try to pair the one electron in the 3D, take one from the S to the D? Do we do that when we're trying to figure this out, or?
Will we take one from the S? I don't really know which of those is the correct structure because we have this shuffling around that happens, right? It's kind of, I'd have to memorize it, and I'm not even sure what technique you used. I'll be honest, I'm not sure what technique you used to determine whether it's in the S or in the D, but I'm sure there is one. But when I look at this, if I was to grade this, right? We talk about this full shells being stable and half shells being stable, right? Well, here I have a full shell and here I have a not full shell, right? And I could take an electron from here and put it there and have this one be, actually, that's a good point. I bet you that this one actually, since I can make a half full shell and a full shell, was that what you saw there? All right, you're quicker than I am with it. Let's see. So I could do that, and then I would have a half full shell and a full shell, and I bet you that's what the actual electron configuration is.
And is both correct? Will we get points off if we don't do that?
If you don't do that, I'd probably try and point it out too. I'd say, remember your half, so we try to make as many half or full shells as possible. For that, if I'm testing that sort of problem. So that sort of thing is really kind of tricky, and I want you to know it's there, and we'll talk about it being, we'll talk about trying to do half fill shells, filled shells, and there's debate about, so half fill and full shells is kind of we talk about models in this class, right, and how models, we have these models that we used to explain things, we try to use the simplest model possible, but our models don't necessarily reflect reality. So I've heard chemists debate about whether it's half full shells and full shells, or really whether it's the fact that you get more charge in the nucleus and it pulls orbitals down. I'm not going to go into that. I'm not going to go into the debate. We're not going to settle it here. We're going to talk about half full shells and full shells because it's a simpler model. But I think I would call, if I was to ask you about this, I would call your attention to it, okay, in the problem, if I was looking for that, because I feel like it's It's a more complicated concept and it's not always right. That makes sense? It's right a lot of the time. Good question. So honestly, if you could do this diagram not even worrying about half full shells and full shells, I am thrilled. Okay? Be able to do those diagrams. That would be awesome. So we're not gonna, I don't want to spend, that was more time than I wanted to spend on half full shells and full shells. Other questions? So don't stress about the half full shells and full shells, and don't really worry about it unless I write in the problem and try and draw your attention to it. All right, so my notes say now I'm going to talk about, we've talked about that, you will need that for lab. All right, I guess you have a pre-lab assignment that talks about it. Let's talk about this thing called valence electrons. And this is pretty easy. We've been using this term already. We just haven't called it valence electrons. These are our outer shell electrons. But we're going to switch our terminology now. Valence electrons means outer shell electrons. And moving forward, I'm going to switch to saying valence electrons. I want to remind you that a covalent bond, because we've had a weekend here, right? Covalent bond. What's a covalent bond and how is it? Don't tell me how it's different from an ionic bond, but tell me what it is. But the definition kind of tells me how it's different from an ionic bond. Yeah, it's a bond where we get shared electrons. A bond where electrons are shared between two atoms. We don't ever get bonds really that we have shared between more than two atoms. Okay, we have this other tool we're using, or this other concept we're using. We're going to use all these things today. It's called the octet rule. What's the octet rule? Yeah.
Outer shell electrons, like when numbers of 8 are especially stable.
Yes, having 8 outer shell electrons is especially stable. Okay. We'll say well, let's say outer shell here. Outer shell. Having 8 outer shell electrons is very stable. Okay, and in our concept with covalent bonds, let's say they generally do this. Atoms generally share electrons to get 8 electrons around them, including the shared ones. Let's say to satisfy the octet rule. All right, we're going to be using all of this today. And then I want to introduce a new term, which we haven't covered based on, right now we're going to be talking chapter 9 today. I think you may have seen this on the syllabus if you look there. We did chapter 4. This author for this book then kind of talks about acids. We don't want to talk about acids and bases right now, where we were just talking about covalent bonds. So now we're going to use that concept to talk about how those bonds are made in molecules. And then we're going to move on to talking about molecule shapes. Okay, use that for molecule shapes. And then we'll jump back to chapter 4, back to where we were. So electronegativity. And this is essentially how much an atom wants electrons. All right, and it's kind of a combination of ionization energies. Okay, it's a combination of ionization energies and electron affinities. So let's go ahead and draw our little Okay. Let's draw our little periodic table diagram here. Looking at the periodic table, what would you think my trend would be if I was to draw a trend of how much an atom wants electrons? Where do you think how do you think it increases based on what we know? Yes.
Down and to the left.
Okay, so down and to the left, it's going to act, that's half of it, so good. So it's I'm going to go to the left, is how much an atom wants electrons. I want you to think about it. So you think, if we go this way, does sodium want an electron? No, it wants to give up an electron, right? Same thing, cesium even more. Okay, so yes, but the opposite. How much does it want an electron? If these guys over here want electrons, they go over, right? And then kind of the smaller they get, the more they want electrons, all right? So, it's actually up and to the right. And this is going to be important for when we talk about who's going to share, right? We're going to share electrons, but then sometimes we're going to have to decide who has to share more, which atoms have to share more, and which atoms have to share less. If an atom wants an electron, it wants to hold on to it itself. It's, you've got a bunch of toddlers in the room, and it's the toddler, it's not sharing its toys. Is it going to want to share electrons more or less? Atom has a higher electronegativity. It wants electrons. Is it going to share more or less? Less, right. So if we have a way when we figure out who's sharing, which atoms are sharing, we have a way to make it share less, that's a better way to design the atom or to model the molecule, I should say. Okay, so this is increasing electronegativity. All right. So what we're going to move on to now is we're going to talk about how Lewis dot structures. Okay, and they're just called Lewis structures in your book. So we've got Lewis dot structures. These are so cool, okay? These are just us kind of thinking about valence electrons and drawing dots and counting to 8. And it tells us how many bonds each atom has to it. And it tells us, and we can use it to tell us what charges are on atoms and what charges are on molecules, okay? And we're just trying dots and quantum counting to 8. Electrons don't look like that. Electrons are clouds. And we've seen our shells, right? They're clouds and they have weird shapes. Well, we have S, which isn't a weird shape. It's just a sphere. We have P's that are these barbells. We have our D's, which are these four double barbells together mostly, and it's the weird one that has like the Saturn ring around it. You know, in this picture. So electrons don't look like this, okay? They're these quantum mechanical things that are really kind of hard to think about. And yet we can have a model, once we're back to our models, we have a model here that is really simple that can tell us a lot, okay? Super cool. Also, super used over and over and over again. All right, so we're going to draw these structures. We're going to learn to draw these structures, but it's really important you learn how to do this. All right, and there is a method. I'm going to teach you the method today, and follow the method. Don't try to do it, just kind of put it together. Okay, just follow the method, and it works. So we are going to use these in here. We're going to use these. They're going to tell us a lot about molecules. And then if you are organic bound, which some of you are, if you're bound for organic chemistry next year, you will use these again in organic chemistry. It'll be super important there as well. All right. And I teach biochemistry, and they are important. The concepts of these are important there as well. But at that point, I kind of assumed, I have you draw them a little bit, but I just assume you kind of know them and you've internalized them and you have enough molecule sense at that point that we don't need them so much. All right, Lewis dot structures. So the point of Lewis dot structures is we're going to connect a bunch of atoms together in such a way that every atom has a full outer shell. Okay. Okay, so in other words, we're going to follow the octet rule here. Except for hydrogen, where we have 2 electrons for an outer shell, for a full outer shell. All right, so I'm going to give you a couple examples and then we'll go into the method we're going to use to do this. So we've talked about carbon dioxide before, right? I have a ton of these just memorized. I don't even need to use the method because I've been doing chemistry for 30 plus years here. Okay, but here, this is what the Lewis dot structure for carbon dioxide looks like. I want to remind you, so then what we do is to see whether this is a good Lewis dot structure or not, I'm going to count up how many electrons are around each atom. All right, each of these count as 1, and then each bond counts as 2. There are 2 shared electrons in each of those bonds. These are double bonds. 1, 2, 3, 4, 5, 6, 7, 8 around this oxygen. 1, 2, 3, 4, 5, 6, 7, 8 around this oxygen. And around the carbon, 1, 2, 3, 4, 5, 6, 7, 8 around that carbon. Okay? Everybody has 8 electrons. Everybody wants to be a noble gas. That's a very stable molecule. Okay, and so probably the structure. Let's go ahead and do formaldehyde. Formaldehyde looks like this. And we'll count for that one as well. All right. This hydrogen. Hydrogen has how many around it for a full outer shell? 2, not 8. So you're only ever going to make 1 bond to hydrogen. Okay, let me say that again. Only ever 1 bond to hydrogen and never put any electrons on it. Okay? So this hydrogen, 1, 2, right? This hydrogen, 1, 2. This carbon, 1, 2, 3, 4, 5, 6, 7, 8. 8, happy. 1, 2, 3, 4, 5, 6, 7, 8 for that oxygen. Okay, that's a good Lewis dot structure. Questions so far? We got the 8. All right, that's where we're headed. Let's talk about the set of rules that we'll use to do this. All right, let's say we want to do, let's say our question was draw the Lewis dot structure for ammonia. Okay, and ammonia is NH3. All right, so what we do first for this is the first rule is we add up all the valence electrons. Remember, that's outer shell electrons. So for ammonia, ammonia has a nitrogen, right? It has a hydrogen, it has another hydrogen, and it has another hydrogen. Number of valence electrons over here. Nitrogen. How many valence electrons does nitrogen have? Outer shell electrons. Look at that periodic table, or get out your periodic table if you can't see it from where you are. 5. Right, okay? So remember, we're going to, the periodic table is your friend. We're going to use the periodic table to get to that 1, 2, 3, 4, 5. Everything beyond, below it or anything above it on the periodic table, above its row, is inner shell electrons, so we don't count that. 5. How many does hydrogen have? 1, right? All right, 1 for each of these. So we have 8. So 8 valence electrons. Okay, great. That's how many we have to play with to make this molecule. Remember that the outer shell electrons, they determine the chemical reactivity. All right, what we're going to do here is we're going to put the least electronegative atom in the middle, okay, but not hydrogen. All right, hydrogen does not make a good middle atom because it only makes 1 bond, right? It's not going to be in the middle if it only makes 1 bond. All right, so in this case, that means nitrogen goes in the middle. So we're going to put nitrogen in the middle here. All right, make single bonds. This wasn't actually listed, I think, in your book's directions, but you got to make when you talk about that, make single bonds from the middle atom to all the other atoms. All right, so I'm going to go 1, 2, 3 to my hydrogens. The next rule is you're going to fill the octets of the other atoms. And this follows ours. So remember, we put our least, it's not going to be so relevant here, but we put our least electronegative atom in the middle, right? The one that's willing to share most. The really electronegative atoms aren't willing to share. So we're just going to give those, we're not going to make those outer atoms share. In this case, it's hydrogen, so it's not, I perhaps should have picked a different example, but we'll do another one quickly after this. So my hydrogens, for them to have filled outer shells, right? How many electrons does hydrogen need? 2. 1, 2, 1, 2, 1, 2. I'm done. Okay? And then fill the octet of the inner atom. Okay? Okay, you might need to share from outer atoms to do it because you'd run out of electrons. I'm sorry, you have to share electrons from the other atoms to do this. Okay. And that's because you ran out of valence shell electrons. All right, questions? All right, so then let's go ahead and do, and then the final one here. Looks like, hold on. I need a 3 here. I need a 4 here. I said it, but I didn't write it down. Fill outer shells of the other atoms. okay, the ones that aren't the middle atom. The ones connected to the inner atom. Or the, yeah. Okay, and then the final thing that we're not going to do right now, we're going to draw some Lewis dot structures, and then we'll worry about this, is you're going to determine or calculate the formal charges. On the atoms. And we'll talk about formal charges and how to use those to figure out the best structure. So for 4, if we go back to 4, I'm supposed to fill in the inner shell atoms. And what I do is I'm not counting as I'm going along how many I have in terms of sharing. You could do it that way. I kind of draw something. I see whether I use the right number of electrons. And if I use too many, then I go back and I draw it again and try again. Okay. So here I've got nitrogen. I've used how many electrons? I had 8 valence electrons to use. 1, 2, 3, 4, 5, 6, 7, 8. I used 8. Okay? This is good. I used 8, and then everybody has 8 electrons around them. Look at the nitrogen. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Does that make sense? So that's a good structure for ammonia. Let's do one that's more complicated. Let's go ahead and let's do hydrogen cyanide, okay? So hydrogen cyanide, so draw a Lewis dot structure for HCN. So what I'm going to do here is, remember, hydrogen's never ends up being, we got to decide what's going to be the center, or actually we're going to add up our valence electrons first, right? So once again, add up valence electrons. All right, so we're going to have hydrogen, and we're going to have carbon, and we're going to have nitrogen. We'll have number of valence electrons. How many does hydrogen have? How many does carbon have? 4. How many does nitrogen have? 5. Awesome. You guys got this, okay? So now that's going to give me how many total? 10 valence electrons. So that's how many I have to play with. All right, second rule. Least electronegative atom goes in the center. Okay, not hydrogen. All right, which one goes in the center then? Carbon, right? Remember, we get a more electronegative as we go to the right on the periodic table and we go up. Remember that electronegativity is how much an atom wants electrons. So by going in the center, carbon is going to have to share more than the atoms on the outside. All right? And it's least electronegative. It wants electrons the least, so it's willing to share more. All right, now I'm going to connect to outer atoms using single bonds. Might not be following exactly my numbering up above, but just make sure you do all of these steps. We're doing them in the same order, okay? Next, fill. I'm going to actually have added a step here. Fill outer shells of outer atoms. Hydrogen, how many electrons does hydrogen currently have around it? 2, so it's good. Do you have a question? Okay. Nitrogen, how many electrons does it have around it? 2, how many more does it need? 6. So we're going to go ahead and do this. All right. Those are all filled. All right, and then you're going to fill, I separate two of these. Fill outer shell of center atom. All right, I'm going to show you two ways to do this. You can decide which you like best. So your book would have you count up your electrons. You would go 1, 2, 3, well, 2, 4, 6, 8, 10, right? I've used all of them. I don't have any more to use, but I still need to get how many more electrons on the carbon? 4, right? I need 4 more electrons, so I need to make 2 bonds to it. I need to share 2 bonds to it. And so what your book would do is you'd move these 2 electrons down into a bond. And we have to do, that's 2, right? But I need 4, so you move these 2 electrons down into a bond. Okay? And so what you'd end up with is this. How do people feel about that technique? Like it? Some people like it. Okay? I'll show you my technique real quick, or what I learned. I kind of like moving the electrons like that. It's kind of getting you ready for organic. You're going to be moving electrons. I would draw this, and then I'd count up how many electrons I used, right? I'd find out I was using 4 too many. So then I'd go, oh, well, I've got too many, so let me make another bond. And then I'd draw this, and I'd find out I still had too many 2 electrons now instead of 4 too many. And then I would draw this, and I'd be okay. All right, you can decide which of those you like, what works best for you. Questions? Okay, and then our next step would be do formal charges. We're not going to do that yet. Let's practice this first before we worry about formal charges. Go ahead and let's draw the Lewis dot structure for, let's do phosphorus trifluoride. Whoops. Actually, I should have just named it so we could get some naming practice. But phosphorus trichloride, let's do that. So follow that set of steps for doing that. And while you guys give that a shot, I'm going to try to get some of your quizzes back to you. Give you a couple minutes. I'll see where people are. How's everybody doing? You need some more time? Okay, I'm gonna. All right, so how would I do this? I'm going to first count up. Remember, the process is important here. If you look at it and say, hey, yeah, that's great, I'll just do this. I really recommend it. Unless, if you can look at all these and just knock them out, great, more power to you. But if you're not always 100% getting them, learn the process, okay? It's just like dimensional analysis. The problems will get harder, and if you know the process that we're using, it will work, and you'll be able to do anything. And if you're using your process and that you're just kind of looking at them and figuring out where to go, eventually you're going to get into trouble. You really probably are going to get into trouble with it. So I really recommend use the process. So what we're going to do is we're going to count up valence electrons. Right, so phosphorus, 3 fluorines. How many valence electrons on phosphorus? 5, right? Count across the periodic table there. How many on fluorine? There's your 7. So 7, 7, 7. Oh, we got a lot of electrons to play with here. Okay, that's great. I always like having lots of electrons. But, so 21 plus 5 is 26 valence electrons, right? Second, put least electronegative atom in the middle. Which one is that? Phosphorus. Okay, so we're going to go phosphorus, single bonds from phosphorus to the fluorines, right? I think I'm going to stop for time here. I'm going to stop writing down the rules again. So what's our next step, though? Yep, fill the valence shell electrons on the outside. So each of these fluorines has 2 electrons on it, right? So I'm going to add 6 to each. Okay, and we're going to try to use the books. I'm going to use the books method here. If you want some help with the method that I used to use, that's great. But I do like this book method. So let's look at how many electrons we have. So we have 26. How many have we used? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I know, because I know where we are. But you want to do your careful. So I've got 2 left. If I put those 2 there, I fill in the inner shell. Now I'll use 26. I've got 2, 4, 6, 8 around there. 2, 4, 6, 8 around there. You see the other fluorines look the same? That's a good Lewis dot structure. Okay. Let's try this one. Do carbon. Let's do this. CS. I don't even know how to name this. Carbon sulfur dichloride. Sorry, I need to put 2 of them in there. Yes.
So wait, don't we already have 26 without putting 2 electrons on phosphorus?
Does it? Did I miscount? So the question is I added 28 essentially, right? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I'm okay. Yes?
Can you explain how you get 26?
How did I get 26 electrons? Good question. So feel free to work out while I'm answering this, but if you look up here, what I did was I added up, I have 7 valence electrons for each fluorine and 5 for each phosphorus, and let's go ahead and count them. Okay. So phosphorus, 1, 2, 3, 4, 5 in the valence shell. Fluorine, 1, 2, 3, 4, 5, 6, 7 in the outer shell. And then you just add up all of the, take all the atoms you have, you add up all the valence electrons, and that's how many you get to play with to make them all. This one is hard, this one's more complicated. Yes. Right, so which one's less electronegative?
So it's like it increases over to the right side.
Right.
So considering that we consider which one's what, which one's farthest in.
That's a good question. So in terms of what goes in the center, which one's less of the electronegative? When you go this way and this way, well, this one's farther down and this one's farther to the left. This one is more farther to the left, is the way I would do it. Your book actually says just take the one that's farthest to the left. Okay, if you look at that. So in that case, this rule. So if you have a tiebreaker, take the one that's furthest to the left in terms of what goes in the middle. So that would be carbon for this one. Okay. Other questions? That was a good question. Didn't realize I'd given you one that, I'm not going to avoid giving you ones like that. So just remember, if you're going to tie break, go farthest to the left. Yes, Tyler.
So would you also just be able to figure out which one to use by which one has the least amount of valence electrons?
I like your rule. I'm trying to think of if there's an exception. I mean, you're always going to, if we take the one farthest over to the left, that's also going to be the case, right? So I'm going to say that's okay. That's a good one. Other questions? People need more time? Let's go ahead and look at that one now. All right, so we said that we need to figure out how many valence electrons we have to play with, right? That's the first bit. So we'll go ahead and make a table here. So number of valence electrons. Carbon has 4, sulfur has 6. I'm just going to fly through this. Chlorine has 7, and chlorine has 7, right? And I'm just counting across the periodic table to do that. For chlorine, we haven't gone farther down. But hold on, I just want to show you. We're talking about the octet rule here. If I gave you bromine, which maybe I should have, but you're already making it more complicated. I don't count these Ds. The Ds are full, they become an inner shell. When you do that, you don't count them. I also have a higher number, right? So we've got the 4s and the 4p, and that's what counts. So bromine has 1, 2, 3, 4, 5, 6, 7. Okay? Don't count the Ds. Or the F's, God forbid you get a problem with that. All right, so we have what is that up to? 24. 24 valence electrons. And so we're going to go ahead and we talked about already, carbon goes in the middle, right? I'm going to go ahead and connect this up to everybody else using single bonds. It doesn't matter where I put each one, okay? We're not talking about shape yet. Lewis dot structures aren't about shape, they're about how many bonds. We will use them later to help us determine shape, but we're going to have to add something else to that. All right, now I'm going to go ahead and give everybody valence electrons here. Fill these things up. And now I'm going to count how many I used. Yes.
Answer your question. You have 24. Here was my question.
Yes.
Does it matter which one makes the double bond?
It does. Which one shares? Okay. Which one do you think is going to? If we have to choose, so you're ahead here. We're going to have to make a double bond. If I have to choose between one of these two sharing, which one is going to share? Sulfur. And that's because it's less electronegative than chlorine. It's more willing to share, right? Farther over to the left. So you guys are ahead of me here in terms of, I'm going to count up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've already used all my electrons, but I need to give one more pair to carbon, right? So somebody has to share, and it becomes sulfur because sulfur is electronegative, or less electronegative. It's more willing to share. So now I'm just going to rewrite this. Not in red. So I'm going to end up with this. All right, and as a final check, I'm going to practice counting to 8. 2, 4, 6, 8 around chlorine, it's happy. 2, 4, 6, 8 around chlorine, it's happy. 2, 4, 6, 8 around carbon, it's happy. 2, 4, 6, 8 around sulfur, it's happy. Okay? Questions on that? All right, let's talk about determining formal structures. Formal structures, formal charges. All right, the book uses this equation. So a formal charge is a charge. If an atom has more electrons on it in this model, if it has more electrons on it than it has valence electrons, then it's going to be negatively charged. If it has fewer, it's going to be positively charged. None of the molecules we've drawn yet have had a formal charge. But formal charges are going to be equal to formal charge, and it's a per atom thing, is equal to the number of valence electrons on that atom minus the number of bonds on that atom minus the number of unshared electrons on that atom. So I'm just going to put on that atom. And what I mean by that atom is we're going to evaluate each atom separately. All right, this is the formal charge of an atom. Okay. To demonstrate this, I'm going to take, so let's take nitrate. Remember, nitrate's one of our polyatomic ions. It's a molecule and it's charged. Okay. So we've got covalent bonds, and then it makes ionic bonds with something else. But to help us along here, I'm going to draw the Lewis dot structure real quick. Okay. Actually, I'm going to show you something. So I'm going to draw this. I'm going to draw the Lewis dot structure real quick, but I'm going to show you something that we have to do here. All right. So I've got, because I have a negative charge on there, I have all the valence electrons of these. Plus, I have to add an extra one because I have a negative charge, right? So what we could do is, let me not do it as an electron there. Let me do it as minuses, okay? And then we could have pluses on a molecule, all right? And so we have nitrogen has 5 valence electrons, 6, 6, 6, and we have 1 negative charge, and we have 0 positive charges. All right, so we have charges we have to either take away. If I had a positive charge, I would take away an electron. If I have negative charges, I would add an electron. Does that make sense? Okay, so for this one, we're going to go ahead and do this. So I've got, it looks like 18 electrons right, to do this? 18 electrons. And if I remember this, because I've done so many of these, I think I have them memorized. I think I'm going to end up with this. All right, let's see if I'm right, because I might have forgotten it. So I have, what we had? We had 18 total electrons. Valence electrons like that. So let's go ahead. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Hold on. 2, 4, 6, 8.
It should be 24 valence electrons.
Thank you. Yeah. I can't do math. I appreciate it. You saved me at least 30 seconds looking confused. All right, so 24 valence electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Great, I remembered it, okay, even if I forgot how to add. But so we've got, this is our molecule, this is our good Lewis-Dot structure. What are the formal charges on these atoms? All right, so let's go and we'll start with this oxygen here. Formal charges. Formal charge is equal to number of valence electrons. How many valence electrons does oxygen have? 6 valence electrons. How many bonds do I have to that oxygen? 1, 2. Okay? 2. How many unshared electrons do I have? 1, 2, 3, 4. Like that. Okay? Do you see that? All right, so now that means that this has a formal charge equals 0, right? This has a formal charge of 0. How about this one? Formal charge is equal to 6 for oxygen again. How many bonds to it? Come on, you guys want to get on time, right? 1 minus how many electrons does it have on, unshared electrons does it have on it? 6. You guys see this? 1, 2, 3, 4, 5, 6. Okay? 6. So it is a formal charge of -1. All right? So if I was drawing this molecule, I would put a negative charge there, like that. Do you see that this oxygen's the same? Okay? -1. All right, and then the nitrogen. Here, we'll do it in green so we don't get confused with our arrows. Nitrogen, formal charge. How many valence electrons on nitrogen? 5. Minus how many bonds to it? 4. Minus how many unshared electrons? 0 equals +1, right? And so this is going to have a +1 charge here. So we actually get our -1 charge by having 2 negative charges and 1 positive charge. Right? That's how formal charges work. I'm going to tell you right now, but we'll go over a couple more of these on Wednesday when we start out. The most stable structure, so you can draw all sorts of Lewis-Dot structures that are valid. The most stable one is the one that minimizes the charges. Okay? This is still the most stable structure, please. All right, you guys have a good couple days.